there, my ATSEVS533 students. This is Dr. John Schragi welcoming you to the fifth lecture of Module 2 in our class, Lecture 2E, in which we're going to be talking about something that we've kind of been neglecting so far, and that is the whole business of water vapor in the climate. Now, this module, of course, the name is a little bit misleading. It's called the physics of climate, but really we're only focusing on one aspect of the physics of climate, and that is to say, radiation. A true, graduate level class in the physics of climate would get all interested in all the interesting ways that, cyclones and anticyclones transport heat around the world and so on. But really, we're kind of talking about just the core issue, and that is to say how different trace gases in the atmosphere are changing temperatures and globally and regionally, and then the impacts of that, like changes in the amount of water vapor in the atmosphere and so on. But there's sort of been this gorilla, is that the right word? No, the elephant in the room. And that is to be the fact that water vapor itself is a greenhouse gas. That's a complication because, we measure methane, which is an anthropogenic greenhouse gas in the Earth's atmosphere, at least a lot of it is anthropogenic. We measure methane on the order of parts per billion. And we, as in for every billion air molecules, a small number of them are methane molecules. And we measure carbon dioxide, another gas that has anthropogenic sources. What is its units? Parts per million. But, water vapor is kind of a different beast. It's vastly more abundant than those gases. Don't get me wrong, even under really humid conditions, no more than 1 or 2% of a sample of air is made up of water vapor molecules, but it's vast. That's several orders of magnitude more than the other greenhouse gases like carbon dioxide and methane and so on, not even to get into things like nitrous oxides and halocarbons and things like that. Well, good grief, there's a huge discrepancy here. We have this one, like I said, literally orders of magnitude larger. And just to pull a sentence that came from that part of the IPCC report that you read, what they actually said was, as the largest contributor to the natural greenhouse effect, water vapor plays an essential role in the Earth's climate. Notice that word largest? Wait a minute. That's kind of a weird thing, right? Scientists don't usually forget to mention the biggest, right? Something strange here. Why have we not been talking all that much about water vapor as a greenhouse gas if it is the largest contributor? Oh, but to the natural greenhouse effect. So we're not talking about anthropogenic. See, here's the deal. Let's actually run some numbers here. Different sources are going to give you slightly different numbers and so on, but just to give a vague idea, the total amount of water vapor in the Earth's atmosphere contributes a radiative forcing. We could actually compute, the difference in the radiation budget of the Earth before, without water vapor, and then with the observed amount of water vapor, and you get a whopping 75 watt per square meter radiative forcing. Remember those numbers that we've seen before for other radiative forcings? They were often smaller than 1 watt per square meter. Sometimes they were smaller than 1/10 of a watt per square meter. This is huge. The water vapor, the radiative forcing driven by the fact that water vapor is a greenhouse gas is enormous. Just for comparison, the total radiative forcing by carbon dioxide is about 32 watts per square meter. Now, wait a minute, that doesn't sound like a familiar number. We've been talking about radiative forcing of carbon dioxide this whole module. Keep in mind, the radiative forcings of carbon dioxide we've been talking about have not been without carbon dioxide in the atmosphere and then with the observed amount of carbon dioxide. They've been pre-industrial, where the concentrations were in the ballpark of 280 parts per million, and current, which was 400 parts per million. They were just the increase. They were the radiative forcing driven by the increase in, due to anthropogenic sources. The total amount of carbon dioxide has a radiative forcing of about 32 watts per square meter, with the anthropogenic part of that having only about 2 watts per square meter. It's complicated why it doesn't scale quite 1-to-1 the way you might think it would. The point is, though, look how much bigger the radiative forcing associated with water vapor is. In fact, again, the reading that you did in Chapter 8 of the Climate Change IPCC report said the contribution of water vapor to the natural greenhouse effect relative to that of carbon dioxide depends on the counting method. In other words, different studies are going to come up with slightly different estimates of the radiative forcing. but can generally be considered to be about 2 or 3 times larger than the effect of carbon dioxide. Oh, so wait a minute. Again, we don't often just sort of skip something like this. What's going on here? If a certain grumpy old man, I can't say that I know anybody like this, wait, I do know lots of people who are like this, would then say, even if you want to believe in like greenhouse effect and all that kind of stuff, which of course we do, but I'm just saying, even if you were a scientist, you could say, why are you worried about the anthropogenic greenhouse gases? Their radiative forcing is tiny compared to the one of water vapor. I know plenty of perfectly good scientists who come up with opinions like this, who are saying, look, you're worried about, why do you even bother making regulations on things like nitrous oxides or chlorofluorocarbons or something like that? Their radiative forcing is orders of magnitude smaller than that of water vapor. Well, that's not necessarily, no, it turns out to be wrong, but one can see why you could get that opinion, okay? This guy could be hollering further. See, in the real world, we're not, look at this. This is a map, for example, here. This is a satellite image. It's a water vapor satellite image, meaning that it is showing measures of how much water vapor is in the atmosphere. And you can't read the scale and stuff like that. It's too small on this diagram here. But suffice it to say, it indicates that there are parts of the atmosphere that at that particular time that were drier and parts that were more moist. I think we can all agree that there are places on Earth that have less water vapor, like deserts, and places that have more, like rainforests, and that they, volumes of air move. The exact amount of water vapor varies from place to place, and it varies from day to day. And a grumpy old scientist who might even really know a thing or two could easily say, why are we worried about that then? Why are we worried about this tiny little radiative forcing from greenhouse gases that are anthropogenic when there's this huge variation based on the water vapor in the atmosphere? Clearly the greenhouse effect is very the greenhouse effect, the natural part of it, is very different over a desert where there's very little water vapor than it is over, say, a rainforest where there's a lot of water vapor. Plus, grumpy old scientist here could tell the kids to get off his lawn and say, while we're at it, how much are we really in control of how much water vapor there is in the atmosphere anyway? If little changes in the amount of water vapor in the atmosphere actually result in a huge radiative flux, radiative forcing, why are we caring about the radiative forcing due to halocarbons, or stratospheric aerosols, or tropospheric ozone, or any of these other things? Well, again, it turns out to be wrong, but you can see that this is with good intentions to get to the bottom of how this is going to work. Again, I'm not inventing this straw man argument that we have right here. In fact, our good friends who wrote the IPCC Assessment Report 5 used exact verbiage. They said, additional water vapor, we do have ways to put it in the atmosphere. Additional water vapor is injected into the atmosphere by anthropogenic activities, mostly through increased irrigation or through power plant cooling. When they cool down those fins or whatever, they give off a lot of water vapor. Also the combustion of fuel. Most fossil fuels, when they burn, one of the byproducts is water vapor. We do have some mechanisms of putting water vapor in the atmosphere in an anthropogenic way, but I don't have a preconceived idea as to how big that is compared to like the natural variability. It's a fair question. Again, the IPCC report asks it themselves. One may question why, if there's so much focus on carbon dioxide and not on water vapor as a forcing for climate change. And that kind of brings us to something that we talked a little bit about back in the first module of the course when we were talking about climate change and the amount of water vapor in the atmosphere. We need to dig into this better. What does actually control the amount of water vapor in the atmosphere? I mean, if water vapor is a greenhouse gas, in fact, apparently it's the most important greenhouse gas, I guess we better understand what's controlling how much of it there is in the atmosphere. And this is going to turn out to get to the bottom of this issue that the crotchety old man was in the corner of the screen there. Not me, that crotchety old man. What was he complaining about? But we'll get there. See, we have seen a few things that kind of get us on the path of how this is going to work. We have some hints. One has to do with this business of the residence time of water vapor. The truth of the matter is each individual water vapor molecule in the atmosphere, right there in the room with you right now, they don't last in the atmosphere very long. It's actually pretty fast how water vapor gets turned back into liquid water and gets dumped back on the ground and it's out of the atmosphere. Average is about 10 days. Okay, that's just not a lot of time. Within a few days, any given water vapor that's in the atmosphere now is going to be removed by precipitation, which means if you're going to have an overall steady amount of water vapor in the Earth's atmosphere, maybe not at any given place, but worldwide, like the total amount of water vapor in the atmosphere, if you want to just sort of, to a first approximation, say it's probably steady, then we got to figure out how we're replacing it. How we get water vapor back into the atmosphere will be part of the story. Well, we actually already know how you get water vapor back in the atmosphere. It's called evaporation. It happens all over the surface of the Earth, especially on that 70-some% of it that's ocean. And we've already seen, back in Module 1, what it is that controls the rate at which that's happening. Now, in fact, it's a couple of factors, like the speed of the wind and so on, but the single biggest was temperature. Okay, so part of the story of what's controlling how much water vapor in the atmosphere clearly has to be about temperature, because temperature is going to be controlling how fast we can put water vapor back up in the atmosphere. Right? Because it's going to all fall out. Once it falls out, it's gone. Okay, so temperature's got to be part of the story. Back in Module 1, we also saw an equation. We didn't actually do anything with the equation itself because it's horrible. It's actually not so bad. Atmospheric scientists certainly see worse equations all the time, but it's a pretty horrible one, and that was the Clausius-Clapeyron equation. And the Clausius-Clapeyron equation was this relationship that we even talk about in like the intro class, where we are comparing how much water vapor the air can hold to the temperature. It turns out temperature is the primary factor that determines how much water vapor air is capable of holding at a given time. This is related to the whole concept of saturation and so on, if you remember back to your days in ATS-113. Well, wait a minute. Remember that curve? It always showed that the shape of the curve is interesting. The shape of the curve shows that as temperature goes up, the amount of water vapor the air is capable of holding always goes up. It increases monotonically, to use words from like math class and so on. So again, we see a connection between there being more water vapor in the atmosphere and temperature. I mean, I guess strictly speaking, what we're seeing here is that the atmosphere could be holding more. You know, the physics of the gases, the physical chemistry and so on is such that they could actually support having more water vapor molecules in there. We're not going to get into the whole business of how that all happens. That's a physical meteorology topic. But see how we've hit it again? We've hit another way of saying the temperature is part of the story here. Temperature's got to be a big part of the story as to how much water vapor there is in the atmosphere. Not only does the temperature of the atmosphere determine how much it could be holding, but temperature is also determining how fast water vapor gets added into the atmosphere. So even when the air is hot, it can hold a lot of water vapor, and we can put water vapor into it faster. Okay, so temperature and the amount of water vapor in the atmosphere are very tightly related ideas. Okay, that's not terribly shocking. In fact, your book throws some numbers around. It just does a quote again from chapter 8. It mentions that for every extra degree of temperature, I believe they're talking in terms of Celsius here, the atmosphere can retain about 7% more water vapor. 7% more. Now remember, radiative forcing doesn't exactly scale with respect to the amount of water vapor. In fact, it's a little more complicated than that because it's monochromatic, and that term that is the amount of it in the atmosphere is actually that N in the equation for it's Beer's law. It was then in that e to the negative NB delta S. So it's got an e to the in it. It's not straightforward and linear, like that increases the greenhouse effect 7%. But it increases it. Oh, so making the Earth warmer makes the Earth more humid, and water vapor is a greenhouse gas Therefore, it's going to make the planet even warmer. Sounds like we've got a runaway greenhouse effect going on here. But it's actually a little more complicated than that, because remember, as the condensation happens in the atmosphere, that makes clouds. And clouds themselves have a complicated role with regard to regulation of climate in terms of them reflecting radiation, shortwave radiation, and absorbing longwave radiation. Oh my gosh, we got this whole complicated business of clouds here. But there's a take-home message here. And the take-home message is yes, the amount of water vapor in the atmosphere does vary a lot from place to place and from time to time. That's a good point, but it turns out that it's kind of saturated. It's kind of, if you averaged over the whole world, or you added up all the water vapor in the whole world, the total water vapor being held by the atmosphere globally at any given time is actually pretty steady, except with respect to time we see a trend going up. But the total amount being observed from day to day or month to month is actually fairly steady, just steadily increasing. Because the average temperature of the planet doesn't jump up and down radically from year to year. So the total amount of water vapor that's being held by the atmosphere doesn't jump around all that much from year to year. In fact, that trend, with respect to time, in the amount of water vapor, of course, is just very closely related to the global temperature. As the global temperature has been increasing over the course of the last century, we observe that the amount of water vapor, total, planet-wide, certainly maybe not hour by hour or even day by day, but averaged over fairly long periods of time, the trends in the total water vapor in the atmosphere pretty much match the trends in temperature. So, increasing the global temperature results in more water vapor in the atmosphere. Okay, we've seen that there's a couple reasons why that should be. Clausius-Clapeyron equation, the business about evaporation. Okay. So if increasing the global temperature results in more water vapor in the atmosphere, and that water vapor itself is itself a greenhouse gas, pushing the temperature even higher, we get a phenomenon that is well understood in the context of climate science called the water vapor feedback. The water vapor feedback is a positive feedback. It is saying that as we make the world warmer, we add more water vapor, which itself is a greenhouse gas, which would make the planet warmer. But it isn't a runaway greenhouse effect. Okay? It does not just keep growing and growing and growing. Thankfully, our climate system would never have lasted long enough for us to evolve on here if our climate system was that easy to push out to go out crazy, like, for example, the atmosphere of Venus, which has a runaway greenhouse effect. Doesn't involve water vapor, but that's another story. But the water vapor feedback is actually well understood. In fact, I like what it said here in your climate change report. This process, referred to as the water vapor feedback, is well understood and quantified. It occurs in all models used to estimate climate change, where its strength is consistent with observations. In fact, you wouldn't really have a model, whether we're talking a complicated three-dimensional supercomputer climate model, or whether we're talking something simple like our two-stream model that we had earlier. You don't really have a model if it can't handle the water vapor feedback. Okay, there are simple little models that can be, we could add the water vapor feedback, for example, to our two-stream model, and just the math gets complicated fast. We don't need that. But if you can't do it, you don't really have a model. Okay? So the physics and the math as to why this doesn't grow out of control and make a runaway greenhouse effect the way it happened on Venus and so on is actually fairly well understood. We don't need to get bogged down into but these equations converge and all that. That's not the point. Okay. But there's water vapor feedback here. Although an increase in water vapor has been observed, we saw that in the first module, that increase in water vapor has been occurred. That has already happened. This change is recognized as a climate feedback based on the increasing temperature, and should not be interpreted as a radiative forcing from anthropogenic emissions. Now that's a fancy sentence. That sentence would be a heck of a job to diagram. And the take-home message there was this business about water vapor. It wasn't just called the water vapor feedback because that was a pretty name. clearly in the world of climate science we have two separate ideas here. This idea of a feedback and the idea of a forcing. And that verbiage from the IPCC report made it clear that we're treating water vapor as a feedback to climate, not as a forcing of climate. Now, grumpy old scientist there in the corner, again, not me, him, says, this is all academic gimcrackery. This has nothing to do with anything. It's not the way the real world works. A joule of heat is a joule of heat is a joule of heat. Who cares what gas emitted it? Who cares what gas absorbed it? That's not important. The Earth can't tell the difference. This is not making me think about changing my mind. And I agree this argument hasn't been that compelling yet, but we can see what we can do about this, because I'm going to tell you that there is a difference. A feedback and a forcing are not the same thing, and we do have to treat them mathematically differently, and we do have to treat them in terms of how we think about them differently, and so on. For example, carbon dioxide. Carbon dioxide concentration in the atmosphere fluctuates both naturally and for anthropogenic reasons. We've talked about this before, of course. And those reasons are not caused by temperature. Oh, don't get me wrong, in the natural environment I can envision that we could talk about slow feedbacks and fast feedbacks that actually are about temperature changing the amount of carbon dioxide in the atmosphere. Let me give you a carbon cycle example. How about the thawing of tundra? Okay, as tundra thaws out, the frozen plant matter that's dead inside of the tundra starts to decompose and releases carbon dioxide. Okay, yes, true. But by and large, anthropogenic sources of carbon dioxide are not being determined by the temperature the way the carbon dioxide that's being released in the atmosphere by melting of tundra is controlled by temperature, right? We don't drive more cars when it's hot than when it's cold. We don't burn more fossil fuels in an El Nino year than a La Nina year, or whatever climate anomaly you feel like doing it. Carbon dioxides are not concentrations, certainly anthropogenic carbon dioxide concentrations in the atmosphere are not determined by temperature. They are what's determining the temperature. They are what is setting up that radiative forcing that through the climate response, what was it, the climate response term or whatever, the climate sensitivity factor, that was the terminology that the book used. They're what's determining the temperature as we approach our committed warming and so on. Therefore, carbon dioxide concentration is a forcing mechanism. It is what is driving the increase in the temperature. It is not caused by the increase in the temperature. It is what is causing the increase in temperature. Water vapor concentrations are different. Water vapor concentrations in the atmosphere are determined by the temperature of the atmosphere. They are a response to the climate change. Now, if water vapor itself were not a greenhouse gas, that's where the story would end. They would be a response. In much the same way we could have other things that are responses to climate change. I mean, I'm sure there's lovely papers out there that talk about something else and climate change in terms of like its concentration in the atmosphere. And maybe it's argon, just to throw out a gas. Okay, maybe argon concentrations change slightly with regard to temperature change. That would be a response. And argon is not a greenhouse gas, so therefore it is a response, and that's the end of the story. But water vapor isn't that simple. Water vapor is a greenhouse gas. So it is a response to the climate change, but it's a special kind of response. It's a special kind of response that amplifies the original climate change. So the anthropogenic greenhouse gases like carbon dioxide and methane and so on create a temperature change that changes the amount of water vapor in the atmosphere, and the amount of water vapor in the atmosphere drives a greenhouse effect as well that amplifies the original change that was driven by those anthropogenic greenhouse gases. The right term for that process is a feedback. It is a feedback, not a forcing. Water vapor concentrations are a feedback. They amplify. This is why climate change, a relatively large climate change, is happening based on a fairly small amount of these anthropogenic greenhouse gases in the atmosphere. I don't have Grumpy Old Man on the screen right at the moment, but that's another thing that grumpy old scientists sometimes say. The actual radiative forcing by carbon dioxide is just not that large. anthropogenic carbon dioxide in the atmosphere had a total radiative forcing of like 1.5 watts per square meter. That's just not that much. But see, it's going to be amplified, it is being amplified by the water vapor feedback to a radiative forcing that is large enough to be making climate changes in our lifetime. Oh. Well, grumpy old scientists aren't likely to change their mind about things. And you might at best get them to go and sulk and say maybe, okay? But they might, you know, maybe we can change minds. That's what we hope for, right? We hope that people are open to understanding facts and, okay, maybe grumpy old scientist feels that way. Now, before we go and talk about this in the context of stratospheric water vapor, let's answer a couple quick questions. Question 1. Water vapor in the atmosphere, blank. A, reflects and scatters long-wave radiation. B, absorbs and emits long-wave radiation. C, absorbs and emits short-wave radiation. Or D, has an optical depth of infinity with respect to short-wave radiation. Okay, well, let's just see what you can do with this one here. Make a choice from those 4 options below this video and get a little feedback before you move it on to question 2.